Hello, very welcome back to our channel, and we are going to explore the functionality of the circuit that is shown on your screen. So as you can see that I have got this VDD power supply. I have got the two inputs A and B, and I have got these four transistors, 1, 2, 3, and 4. And here is the output of this circuit, F. So the upper two transistors, which are connected in this fashion, that is Q1 and Q2, are PMOS. And these two transistors, Q3 and Q4, are called as NMOS. So we can identify them by their symbols. Here you see the bubble on the gate pins, and here you don't have it. So obviously Q3, Q4 are NMOS, Q1, Q2 are PMOS. So let's have a connection understanding. So what you see here, as I said, A and B are the two inputs. So they are cross connected to the gate pins of these transistor NMOS Q3 and Q4. So these A and B that are the input lines are connected to the source pins of the transistor Q3 and Q4. At the same time, A goes to the gate of Q4 and B goes to the gate of Q3. So that's a cross connection as well going to the gates of these transistors. Now at the same time, A is going to the gate of the Q2 and B data line or input line is going to the gate of the Q1. And finally, you see that the source of Q2 coming to this junction where the drains of Q3 and Q4 are also connected, and there is our output data line. So it's obviously a logic circuit, and we want to understand the behavior of this circuit, how this circuit is gonna work. So what you see here, you have got A and B, and we would see when you have A and B, that is the two input lines. So obviously 2 to the power n would be the number of possible input input combination or combinations or connections. So n is the number of possible input combination, and base 2 indicates it's the binary system, or we are using a binary logic which is used in computer. So n is equal to 2 because you have two inputs. So therefore 2 to the power 2 is equal to 4 are the total number of possible input combinations. So they will be 0, 0, 0, 1, 1, 0, and 1, and 1. And then we want to analyze for all these four possible combination, what will be the transistor's condition, whether it is on or off. Okay. So when the transistor is the MOSFET, it is on, we say that it is saturated, and if it is off, then it is cut off. All right. So Q1 and Q2, these are the two upper transistors, and then we'll see Q3 and the Q4, these are the two bottom transistors. And finally, we'll see the output data line, and based on that, we will understand the functionality of this circuit. So first thing first, so let us write this. So here you apply 0 and 0. So obviously the 0 to the base of Q4 makes it off. 0 to the base of Q3 makes it off. So obviously these two switches, Q3 and Q4, are off, but A reaching to the gate of Q2, making it on, is a closed switch. B reaching to the gate of Q1, making it as a closed switch, that is on. So here we can write that Q1 and Q2 are on and Q3 and Q4 are off. But when Q3 and Q4 are off, so they are like an open switch. Both are like an open switch, and these are like closed switch. These are like closed switch. Okay, so F gets connected to the VDD, that is logic high. So we will say that output is connected to the logic high, or that is logic 1. So we will write here that there comes the 1. Okay, now we have to find the combination of the inputs, that is the second combination here, 0 1. Okay, so let's say A is 0 here. Let me write it here. A is 0 and B is 1. So A0 making this transistor off, B1 making this transistor switch on. Okay, and 0 going to the gate of the transistor making this on, and the 1 going to the, not the base, this is the gate of the transistor, making it off. So you see now there is no current flow from the VDD towards F, because this upper transistor Q1 is switched off while it is on. But here is also, there is no path for current to flow, but there is a path towards this, through this transistor Q through. So F gets connected to the input. So, or we, in other way, we can say that Q3 now acts as a pass gate, transferring 0 or connecting 0 to the output F. So the level of F here is 0, because 0 getting connected to the F. But what about the transistor Q1 and Q2? So here we'll write Q1 is off as shown in the schematic, Q2 is on, Q3 is on, and Q4 is switched off. So this is how we saw for the second combination. I hope you are following me with what we are doing here. Now it's time to apply the third combination, which is that 1 here and the 0 here. So 1 makes the Q4 on, 0 makes the Q4 switched off. The 1 goes to the Q2, switches it off, and 0 goes to the gate of the Q1, switches it on. So let us write here. So Q1 is on, Q2 is off, Q3 is off, and Q4 is on. And what comes to the output? So obviously there is no path for current to flow. Therefore, VDD is not appearing at F. However, here is also no path for current to flow because this switch is off. However, the F gets connected, or 0 gets transferred to the F through the Q4 because it is on. So we will see the logic here is 0. Now, final combination. It's time to apply a final combination. So we see that the final combination here is our 1 1 right here, 1 1. So 1 comes to the A, 1 comes to the B, making both the transistors switch on, that is Q3 and Q4. Remember, at the gates of these Q3 and Q4, logic 1 is appearing. At the same time, the logic 1, through these cross connections, these transistors at the gate, they receive logic 1 and these therefore are off. Obviously, there is no current path for F to connect to VDD. However, there is a possible current flow from through these transistor Q3 and Q4, and F can connect to logic 1. So we can write here Q1, Q2 are in the off situations, and Q1, Q2 are off, and Q3, Q4 are on. So now it's time to understand what is the logic level here. For 0, 0, output is 1. For 0, 1, output is 0. For 1, 0, output is 0. And for 1, 1, output is 1. So if we see the Boolean expression for this, F can be written as A bar, B bar, okay, for which logic 1, or A and B. So clearly we see, we can recall our understanding of the basic logic gates. what is this truth table or Boolean expression is representing. This is Boolean expression. Okay, so we can implement this logic. So you have like A and B here. So you can connect the inverters, that is A bar and B bar. And then you have a OR gate coming. So that's your A bar and B bar, right? So here you can connect an AND gate. So here comes A bar and B bar and OR A and B. So here you can say that, okay, this A, that's the B, and I have this gate again here, which is giving me the output A and B. And finally, I am ORing them together to get the final expression of F, which is A bar and B bar, or A and B. So this is basically, we have used this 1, 2, 3, 4, 5 logic gates. In terms of transistor implementation, we have to understand how many internal transistor will be required for each gate. That I leave it as an exercise for you. But in short, this output represents the XNOR functional, XNOR, because XNOR logic gate, okay? XNOR logic, this is the output expression for the XNOR, and symbolically we can represent that logic is like this. Right here, there is a bubble, so A and B, and here you say that XNOR B, okay? So correct me if there is something missing here. And I hope you found this module useful. If you did so, click the like button, share it with others, and subscribe. Don't forget to do that. And stay tuned for more engaging and challenging content like this. Till then, wish you happy learning.